Jai Hind to all. Myself Uma Sharma, Assistant Professor in EC Department of Ajay Kumar Garg Engineering College. Today in this lecture, I'll discuss one of the important topic of Unit 2nd of KEC 501, that is Integrated Circuit Design. So here in this lecture, we'll discuss the designing of active analog filter using the Sallen key filter, and definitely we'll discuss the second order design. So let's see the content of the lecture. Introduction to filter, then we'll discuss the different filter responses, then the Sallen key filter design model we'll discuss over here. Then we'll see how we can implement low pass, high pass and band pass response using the Sallen key filter design model. So one by one, let's discuss these topics. So the first thing, what do you understand by the filter? So basically, filter is an electric element or is a circuit by which you can filter out some specific band of frequency and you can attenuate or block a specified band of frequency. That means we can filter some frequencies while other frequency can be attenuated or blocked with the help of this filter. So there is the simple operation, but here there are so many category of filters by which we can perform this filter operation. Actually, it is the frequency selective circuit by which we can select a specific band of frequency. There are so many applications of the filters, like in communication, AM, FM, in everywhere you will use these filters. The filter block is very important in the communication design, in the field of communication. So if we classify the filter, so there are three broad categories. Depending on the input signal waveform or the nature of input signal, we can classify the filter into two categories: analog filter and digital filter. So the meaning of analog filter is that if the input signal is analog in nature, then the filter is known as analog filter. Analog means if the filter is having these type of input signals, then this filter is known as analog filter. While the digital filters are those filters for which the input signal is in the digital form. There are only two labels, 1 or -1. So depending on the nature of the input signal, you can classify into analog and digital. Similarly, depending on the component used for the designing of filter, we can classify the filter into two categories, passive and active. So if we use only passive components are known as, commonly used passive components are R, L and C. So if we use R, L and C in the designing of the filter, then the filter is known as passive filter. If we use active element along with these passive element for the designing of filter, then the filter is known as active filter. So active element means we are talking about op-amp. This is one of the active building block. We are talking about transistor like FET, VJT. With the help of op-amp, with the help of transistor, we can implement the filter operation, and these type of filters are known as active filters. Similarly, based on the frequency of the input signal, we can again classify the filter into two categories: audio frequency filter and radio frequency filter. If the filter is capable enough to deal with the audio frequency band, then the filter is known as audio frequency filter. Similarly, if the filter is capable enough to deal with the radio frequencies, then the filter is known as radio frequency filter. So these are the broad classifications of the filter. Here in this lecture, I'll focus on the active filter design, where we will use operational amplifier as an active building block. We can design the active filter using transistor also, but here we'll focus on only on the op-amp based active filters. Definitely for the designing of active filter, we need R and C, but we will avoid the use of inductor in the active filter design, because we are talking about integrated circuit, and on IC it is not possible to integrate inductor because of different electromagnetic effect and the weight of this inductor. So it is good to use only R or a very small value of capacitor along with the active element, so that we can reduce the area and we can reduce the power consumption, because area reduction and the power reduction are the primary objectives of the integrated circuit design. So to achieve the objective of integrated circuit design, definitely we focus on the designing of filter using the active building block. So here we will use operational amplifier. So here in detail you can see that active filter contain only the active component like operational amplifier, transistor and FET within their circuit, and also they draw their power from the external power source and use it to boost or amplify the output signal. The meaning of this is that active filters are capable to filter out the frequency. That means the frequency selection can be done using the active filter. Also, we can implement also we can add a feature of amplification. So, active filter are the filter which can select a specific band of frequency and can also amplify the amplitude of the signal, and they are capable to reject the remaining portion of the input signal. So, generally they are used in communication and signal processing like television, radio. There are so many applications of active filters. Other than area requirement and the power consumption, there are some more advantage of using active filter over the passive filter. In case of active filter, because we can vary the gain just by changing the value of R and R1, R2. So the gain and frequency adjustment is very flexible in case of active filter if we compare it with the passive filters. Here I am just talking about the operation use of op-amp. So if I am talking about the use of op-amp, you are already aware that op-amps are having very high input impedance and very low output impedance. So if we are using op-amp in the circuit, so there is no loading problem exists in active filters. Similarly, active filters are cheaper than the passive filter, because here the power requirements are less, component requirement are less, and this is why if we talk about the cost is also low in the active filter when we compare it with the passive filters. Now, after discussing the classification of the filter, this is very important to know about the filter response. So these are the mainly used filter responses in the digital signal processing. There are Butterworth characteristic, Chebyshev characteristic and Wessel characteristic, and out of these three, Butterworth characteristics are the most useful or most used characteristic of the filter. So one by one we will see these responses. So before that, you must know how we can draw the frequency and gain response. So if we talk about the ideal filter, so if this is the frequency axis and this is gain, and there is a pass band and there is a stop band. So this is the pass band and these two are the stop bands. In pass band, we want that this gain must be constant, and stop band, we want the 100% rejection of the frequency, because the filter should be capable enough to reject all the frequency other than the pass band. So ideally it should be like this. If we talk about the ideal response, so this should be like this. There is no frequency selected by the filter in the stop band. Oh, this is the pass band. So this must be the case, but practically this is not possible. So practically we get this type of curve. So this is the portion of this curve only, and in this curve, this is the pass band, this is pass band, and this is stop band. Now one by one, I'll see you what are the, I'll tell you what are the basic difference between in these responses. So first, just talk about a Butterworth response. So in Butterworth response, you can see that the pass band is flat, whereas in the stop band, we are getting a constant roll-off rate. That means the rate of decrement of the gain, and which is 20 dB per decade per pole. So if we are talking about single pole, that means gain is minus 20 dB per decade. But when we talk about, this is for one pole, when we talk about two pole, that means this gain should be 40 dB per decade, and so on. So let's say this is for first order. So this gain roll off is 20 dB per decade. So this is the most useful characteristic in the filter design, because in the pass band we are getting the constant gain. Whereas if we talk about the Chebyshev characteristic, here you can see that in the pass band there are so many ripples. From the green color graph, you can see that the Chebyshev filter responses. So here this filter response is characterized by the overshoot or ripple in the pass band, whereas here the gain roll-off rate is greater than 20 dB per decade. So here you can see that this is the difference between Butterworth and the Chebyshev. Now this curve shifted towards the left hand side, so that means the gain roll-off rate is very high, and this is the desired characteristic. In the step band, we want that this graph should meet the ideal graph, something like that. So Chebyshev filters are having fewer pole requirement. That's why that gives the less complexity to the circuit, because there are fewer pole, so component requirement is less. Now just talk about the Wessel filter characteristic. Here you can see from the blue color curve, here in the stop band, the gain roll-off rate is less as compared to Butterworth and the Chebyshev, which is not a desired characteristic. We want that this graph must shift in this direction to meet the ideal filter response. Whereas if we talk about the pass band, in pass band there is a linear reduction in the gain. So this filter response is characterized by the linear characteristic. So if I conclude that in Chebyshev, Butterworth and the Wessel characteristic, Butterworth characteristic are most useful characteristic. So here in this lecture, we will discuss the designing of second order filter using the Butterworth response. And now you are very much aware with the characteristic of Butterworth response, why we have selected Butterworth for the designing of second order filter. So now come to the designing of Sallen key active filter model. Basically, this is the very popular model which is used for the second order filter design. So Sallen key, the name of the scientist who have given this model by which we can implement the second order response very easily. So just look about the circuit. Here there are 4 passive components which are connected in the circuit, Z1, Z2, Z3 and Z4. There is one active element, that is op-amp. This op-amp is connected in the non-inverting configuration. Non-inverting configuration of op-amp is used. Also you can see that a negative feedback is connected in the circuit. This will provide unity gain to the filter, and if we want to increase the gain of the filter, this can be replaced just by this feedback R1, R2. So if we add this R1 and R2 in this circuit, then this is known as Sallen key active filter model with gain. If we remove this, then this is known as Sallen key active filter model with unity gain. But in this model, these are the components which are responsible to add number of poles in the filter response. So here there are we will connect 2 resistor and 2 capacitor, and just by changing the position of these Z1, Z2, Z3, Z4, we can implement low pass as well as high pass response using this simple circuit. So just see how we can design a low pass filter using the Sallen key active filter model. So from the last slide, you can see that I have replaced Z1 by RA, Z2 by RB, Z3 by CA, Z4 by CB. So these are the 2-pole low pass circuit. This is the 2-pole low pass circuit, whereas the unity gain now has been replaced with the gain of 1 plus R1 by R2, because it is non-inverting configuration of op-amp, and you are aware that the gain of non-inverting configuration is 1 plus RF by R1. So here this filter will provide 1 plus R1 by R2 gain along with the 2-pole filter response. So for the single pole, the gain roll-off rate is 20 dB. So for the 2-pole, it is 40 dB per decade, where this RC circuit, this is known as RC circuit. The input is connected with the RA and feedback is the capacitor. So now if we solve this RC circuit, we can calculate the critical frequency, which is 1 upon 2 pi under root of RA/RB into CA into CB. If RA equals to RB and CA equals to CB, then this expression is converted into 1 upon 2 pi RC. So this is the critical frequency or the cutoff frequency of the low pass filter. So response of the low pass filter will be like this. The filter will pass low frequency and attenuate high frequencies. On x-axis this is frequency and here this is gain, and this point is known as this cutoff frequency FC, and here this gain roll-off rate is minus 40 dB per decade. This is the pass band where gain is constant. So now this is the question how you can design a second order low pass filter. So if the cutoff frequency is given, for the given cutoff frequency easily you can design a second order low pass filter. So these are the steps. Just select the cutoff frequency. If it is given FC, you know the formula that FC equals to 1 upon 2 pi RC. Now with the help of this capacitor, which is to be choose less than or equals to 1 microfarad. This assumption we have taken that this CA equals to CV and that is equals to less than or equals to 1 microfarad. So you can take any value which is less than 1 microfarad and just putting by this value in this expression, you can calculate the value of R. So if you can calculate the value of R, that means you have solved this circuit, RC circuit. We have already assumed that R equals to RB, CA equals to CV. The value of CV we have chosen that is less than 1 microfarad, and by putting the value in the formula, we can calculate the value of RA and RB. So this is how you can solve this circuit. And now in this circuit, these are two unknown parameters which we have to calculate. So to calculate this, just to calculate the value of this gain formula, just a second. To calculate this, just use this formula, because the gain of the filter is given by 1 plus R2 by R1 or R1 by R2. For the Butterworth filter, this is given by 1.586. So this is constant for the Butterworth response, Butterworth filter response. This gain is 1.586. So this is how you can calculate the value of gain, the value of R2 and R1. For this, definitely we have to assume the value of R2 or R1. So just by selecting the value of R1, the value of R1 less than or equals to 100 kilo ohms, you can choose any value which is less than 100 kilo ohms. You can calculate the value of R2. R2 you can calculate just by using the formula. Now just see, R2 by R1 will equals to 0.586 and this R2 will equals to 0.586 multiplied by R1. So this is how you can calculate R2. So this is the procedure by which you can design a second order low pass filter. You can see this example here. Critical frequency has been asked. For this circuit, you have to calculate the critical frequency. The value of RA/RB is given, the value of CA/CB is given, the value of R2 is given, R1 you have to calculate. So it is very simple. You know the formula that FC equals to 1 upon 2 pi RC. You know the value of R and C. So very easily you can calculate this critical frequency, that is FC equals to 1 upon 2 pi RC, and that is equals to 7.23 kilohertz. I have already told you the value of R1 by R2 is 0.586 for the Butterworth response. So if you are designing Butterworth response, then this value is 0.586. Otherwise, you can design a filter for any given gain. So by using the value of the Butterworth gain, you can calculate the R1, which is 0.586 of R2. Just assume the value of R2. You can calculate because R2 is given in the circuit, that is 1 kilo ohm. So R1 equals to 586 kilo ohm. So this is how you can solve the problem based on designing of low pass filter. Similarly, now let's see the designing of high pass filter. In the same way, we can design a high pass filter where I have replaced RA/RB by CA/CB. I have replaced the position of the resistor and capacitor. Just by interchanging the position of resistor and capacitor, now you can see that the two-pole high pass circuit is designed. So this is the RC circuit for the second order high pass filter, and the gain port, this is the gain circuit, and this gain circuit is same for low pass as well as high pass. So there is a small change in the frequency selection circuit. So in frequency selection circuit, we have just interchanged the position of RA/RB and CA/CB. So here also the gain roll off rate, because it is second order filter. Why second order filter? Because it is having two pole, because there are two frequency dependent component are in the circuit. So that's why it is two pole circuit, and the gain roll off rate is 40 dB per decade. In the same manner, you can calculate the critical frequency for the Sallen key high pass filter, and this comes out FC equals to 1 upon 2 pi under root of RA/RB CA/CB. If we assume RA equals to RB and CA equals to CB, and that is equals to C, so this equation comes out FC equals to 1 upon 2 pi RC. So this expression is same for low pass as well as high pass filter. So this is the beauty of second order Sallen key filter, where the critical frequency is same for low pass as well as high pass filter. Now you can see the response of high pass filter. So this is gain and this is frequency. So the filter will pass high frequencies over and that will attenuate the low frequency. So all the high frequencies will be passed through this filter, but the filter will attenuate or stop the low frequency. So this is the stop band and this is pass band. So the gain roll off for this response is minus 40 dB per decade. So here it is not minus, actually it is plus, because gain is increasing with the rate of 40 dB per decade. Initially the gain is 0, then it is increasing, and at the critical frequency gain is constant, and this gain can be given by 1 plus RF by R. This is the gain of the filter. Now with the help of low pass and high pass filter, the next classification, which is active band pass filter, it is very easy to implement. So before starting the designing part of this active band pass filter, just see what is the response of active band pass filter. So band pass filter means the filter that will pass a particular band of frequency and attenuate the other frequency band in the low pass and the high pass. So here you can see that this is the low pass band, means this is the low frequency band, and here is one stop band in low frequency band and another stop band in high frequency band, and in between there is a pass band in which all the frequencies are passed with equal gain. So now if you see this graph or these characteristics, you can identify this is the combination of, this is the addition of two characteristics. You have seen in the previous slide that this is the graph for high pass response, and for the low pass also I have drawn the characteristic. So if I add these low pass characteristics just after the high pass, then definitely I'll get the frequency response of band pass filter. If I add a low pass response in series with the high pass response, then definitely I can achieve this response. So band pass filter is formed by cascading two-pole high pass filter and two-pole low pass filter. There is a condition that both the filter must have same order. So both the filter high pass and low pass should have either first order or second order. The order must be same. So for the designing of second order filter, this should be two-pole high pass filter and this should be two-pole low pass filter. And definitely we are talking about the Sallen key Butterworth configuration. So you can see that just I have added the previous high pass filter in this slide, which is having two capacitors CA1 and CB1, two resistor RA1, RB1, which are connected at the non-inverting terminal, and at the inverting node there are two resistor R1 and R2 that will provide gain to the circuit, gain to the filter, and the output of this high pass filter is going in the low pass filter. And again you can see that the components are same. The position of capacitor and resistors has been interchanged. So RA2, RB2, CA2, CB2. Similarly here this R3 and R4 are added to produce the gain for the filter. And definitely this gain must be constant for all the filters. So in that case R1 must be equals to R2, must be equals to R3, must be equals to R4. So this is how you can design the band pass filter. And here in this slide you can see the characteristic of the band pass filter, where this is pink color line is representing the low pass response, whereas the blue color line is representing the high pass response. The gain roll of rate is same in for the high pass response, which is represented by the blue color line. It is 40 dB per decade because gain is increasing. For the pink characteristic, that is for the low pass filter, this gain roll of rate is minus 40 dB per decade because gain is decreasing. Here there are two critical frequency, FC1 and FC2, and the FC1 is the known as the lower cutoff frequency, whereas the FC2 is known as the higher cutoff frequency, and definitely FC2 should be greater than FC1. Then only you can achieve this curve. Otherwise you can not achieve this type of curve. The dotted line are representing the ideal response of a band pass filter. You can calculate the cutoff frequency F0, which is equals to under root or square root of FC1 into FC2 here in this slide you can see that all the formulas. FC1, because you know already that it is the FC1 is the cutoff frequency of the high pass filter, so it can be given by 1 upon 2 pi RA/RB C2, and for the FC2 this is for low pass, and this is how you can calculate the critical frequency for the active band pass filter, and this is the for the equal component filter, this is the critical frequency, that is 1 upon 2 pi RC. So this is how you can implement low pass, high pass and the band pass response with the help of Sallen key active filter model. So this is all about the designing of second order filters. Thank you so much.